Hi,
Hey, Matt.
can I see your solution? Can I see your solution?
Well, um, the the obvious easy formula for Sn is going to be n plus one factorial.
Yeah, of course.
But basically, you can just use counting to factor it into 1 plus 1 times 1 plus 2 times 1 plus 3, all the way up to 1 plus n. So
Cool.
you don't have to do an induction if you just start with this expression and then say the use like the same argumentative reasoning as the binomial theorem to say that this will produce all those products of the subsets of 1 to n.
Okay.
Whereas, yeah, so if you have a 1 in the if you're choosing a 1 from a set of parentheses, then that's the same as not including an object in
Yeah.
your subset.
Okay. What was your induction proof?
Um, so if we have a set, let's say S is the letters A through N, then let me see if I remember this font. It's like, oh, am I going backwards? I don't know how to do the power set sign anymore. I used to know how to write it. It's like Weierstrass P, power set of S.
Oh wait, I don't see anything.
Ah, yeah. I guess what happened is I just left it
Okay.
on active inspire, but then I remembered the rage that active inspire makes me feel every day. Um, Here we go. Oh, also, I'll show you this proof. Oh, so you weren't able to see this. You factor it this way.
Yeah. That I think that was mine. Instead of factoring it or instead of using your logic, because I'm not entirely familiar with that. Uh, you can split it into like a factoring argument.
Mhm.
So the sum of all the factors of an integer is or there are like if you have like 2, 3, and 5, it's 2, like 2 to the 1, 3 to the 1, and 5 to the 1. It's 2
Yeah,
plus 1 times 3 plus 1 times 5 plus 1.
yeah,
So
that's related to
because
generating functions.
yes,
The sum of divisors formula and then the relations to generating functions is very, very intensely interesting. That's the logic that I'm using here, though.
yeah, I think that's how I did it. I didn't do it the way you did because again, I'm not familiar with this.
Okay, yeah. So you have to pick one number from each of these pairs, right? When you do the product for all the terms in the monomial before you add them up. So picking a 1 from one of these parentheses is the same as not including that element, the other element in the parentheses in a subset. But
Yeah.
yeah, so the distributive law is just extremely powerful for counting, and is actually also responsible for Taylor series and the connection between Taylor series, generating functions, some of divisors formula, or some of kth powers of divisors formula. Um, like when k is equal to 0, that's the number of divisors formula, is also operating on the same exact magic that is the distributive law. But so the power set, if we have a set A through N, then the power set of S is the set of all subsets of S, including the empty set and itself. And the size of the power set of a set is equal to 2 to the size of the set. And the reason that this is true is that when you can,
Can't this be shown with a Pascal's triangle?
yes,
Yeah. Okay.
yeah. The way that I think about it though is like, so let's say we start with the empty set, then that's just 1. The
Oh
power
yeah,
set,
everything's either in a set or not in a set.
yeah. No,
Oh,
maybe. That's a really philosophical question, which we don't
no,
have
no,
to.
not what I mean. Like it can be represented by binary. Like if 0 if it's in the set, 1 if it's not in the set. So you have
Yes.
2 however many
Yep.
things.
Um, but I should actually have the empty set in here and the set with 1. Let me just write out a few examples of this and also show the relationship to cube geometry. So we can just imagine this as a single point in space. And then we can imagine to create the power set of the next one, we take a point in space and then we draw a line to the power set that we had before, union with our new thing. So when we create the power set of 1, 2, we have the empty set, the set with just 1 in it, the set with just 2 in it, the set with 1, 2 in it. We can imagine taking this original power set of the one before, which I'm just going to simplify. Excuse me. And adding on this new bit where we add the new element into all the previous ones. And this is the same thing as happening in binary, same thing that's happening in Pascal's triangle. But this is just how to think of it in terms of power sets and why the size is doubling. And that is also explaining why we're going to have that S of n plus 1 is going to be equal to S of n plus n times S of n plus, S of n. So that's when I first thought of it, this is the induction proof that came to my mind.
Yeah, that makes sense.
Okay, so let's look at this integral. We're able to figure out the trick?
I was not.
All right. So let me rewrite it here. Actually, I will rewrite it here, and then I'm going to come up with another one that uses the same observation to solve it and could potentially be very annoying otherwise. And that'll give you time to take another crack at this one. Because there is just a very simple thing that you can see that will blow this thing wide open.
The derivative of 1 is the other. Or is it
No,
very close to another?
you're thinking in the right direction.
It's like the rule. I forgot what it's called, but like if it's AB, then it's A prime B plus B A prime.
Ooh, I think you got it,
Called
Ashford.
multiplication rule.
So
Oh
Yeah,
yeah,
multiplication
it's
rule.
in that. It's the
product rule.
Product rule.
How is the product rule related to power sets in the binomial theorem? Because it almost is exactly the same thing we were just talking about, actually. So what we have is that this thing is equal to so that's just equal to x squared secant x. All right, so then try the integral of this thing, minus 3 sine of x over x to the 4th plus cosine of x over x cubed dx. So the stupid thing to do would be to split this apart and then use integration by parts like roughly 7 times to solve this. It sounds like it would be pain, and I would also be extremely interested in seeing how that would collapse back down into the incredibly simple answer that we can get.
This is also a
Yeah,
a
it's
product
like
rule because one over x,
Essentially,
yeah, x to the -3, and then -3/4 x to the -4. Just one's the derivative of the other, or no, yeah, but sign goes to negative cos.
it's essentially
Or
just the
sorry,
same
cos
thing.
goes negative sign.
What happens when you take the derivative of this? You get a -3, and then it drops to x to the 4th in the denominator.
Yes.
Yeah. Yeah. So that's a pretty good integral. And so they like to do this kind of trick in integration bees. I've just been watching integration bees to fall asleep, honestly. And it's also sometimes interesting to see how people behave on the spot when they can't come up with integrals like 3 times in a row. But they have some good integration tricks in integral bees. So let's see now just some more integration by parts stuff, which isn't necessarily a standard integral that you would run into and requires a little bit more clever thinking to solve. All right, so the integral of x times tan squared of x dx. Yeah. So one of the things that you might be noticing at this point is that you're having trouble doing integration by parts with this thing, with the tan squared. But if we rewrite tan squared of x is equal to secant squared of x minus 1. Yep. Then we get the integral of x secant squared x minus x dx. So this is going to be minus x squared over 2 plus the integral of x secant squared of x dx. And this thing might be easier to work with. So what at this point, I'll spoil it. We should do integration by parts. What are we going to set to u and dv?
U is x, and then dv is x squared. And then I got f prime of x. Or sorry, yeah, I guess dux. I should have said that. The derivative of it essentially is 1, and then the antiderivative of the other one is tan. And then I didn't get time enough to solve. But I also don't know how to integrate tan.
Really? Okay. So we have plus x tan x. Oh, there should be no dx here. Why can I just when we did this thing right here, we really should say du over dx is equal to 1. And then I did a physicist move and just rewrote it as du equals dx. And if I didn't justify why I did that, it would be an extreme physicist move, an engineering brained pill moment, but if we ever get to a combinatorial discussion of Taylor series, then we can see that that this equation we can arrive at independently without thinking nonsense about infinitesimal fractions. So here, then we do the integration by parts v du plus 10x dx. So that should be a minus sign.
You've explained how to do like the integral of 10x before, but I always forget.
Yes.
Yeah,
And
that's.
then I'm too dumb to actually do it myself.
How about if I wrote it like this? Set u equal to cosine x du equals to minus.
Oh, so it'd be negative ln cos.
That makes sense.
Right. Forgot about that. Now I feel dumb. Damn it.
It's all right. In my class, I'm not giving you grades. You will have plenty of opportunities to not remember these on a test. I'm sure that I have failed to remember integrals like these before. So there was a minus here and minus here, so this should be plus ln cosine x. Absolute value thereof. Just got to be careful about that. All right. The next one on my list is the integral of arc sine of x over the square root of 1 plus x dx. Yeah, in general, there's like no unified theory of how to like algebraically manipulate integrals in order to obtain closed expression for antiderivatives. And it's actually known that there are plenty of that's a rabbit hole that's called real analysis, basically, and not necessarily finding algebraic manipulations to solve integrals, but proving when certain integrals can be algebraically manipulated is what real analysis is. Like, that's the whole driving force between it. Everything else is kind of just philosophy that fills in the gaps. So this one, what is my du and my dv? Or u and dv?
I set u as arc sine.
Yep.
X, and then du is 1 over, I think, square root 1 minus x squared.
Yes.
And then I set dv as a denominator.
Yep, that should be dx over 1 plus square root of 1 plus x.
My bad.
So then v is equal to, gosh, I have to integrate that. Okay, so integral of 1 plus x minus 1/2 dx. So that should be x 1 plus x to the 1/2 over 1/2. So that's 1 plus x to the 1/2. Did I do that correct?
Yep.
Okay. So then we get that this integral should be 2 times the square root of 1 plus x times arc sine x minus the integral of, so it feels off to me, but we'll continue. 1 plus x. I guess I better make that a square root for brevity. Square root 1 plus x for square root 1 minus x squared dx. Okay, and we can simplify this into an integral we can solve. Dx over square root of 1 minus x. Should that just be minus what I got for this thing right here? Let's check.
Yeah, but then, yeah. With a minus in the parentheses as well.
Yeah. So would the minus signs cancel out and it becomes a, yeah, and minus sign in the
Yes.
parentheses as well, yeah. Let me just double check. So then we should have a 4. Okay. So we get this is integral is 2 times 1 plus x arc sine of x plus 4 times the square root of 1 minus x plus c. All right, and the next integral. All right, square root of x squared, and let's do plus or minus a squared because it doesn't make a difference what the sign is. We'll just carry the plus or minus through the formula. All right.
Or wait, are we deriving with a as a constant?
Yeah.
Or
Oh yeah, a is a constant. Well, you wouldn't even a could be a function, but it's constant with respect to x. So
okay, yeah, that's what I meant. So would u substitution? Wait, why would integration by parts be required here?
why wouldn't? No, integration by parts is required here.
But why?
Um, well, the y answer is there's no algorithm to tell you when integration by parts is required, but something like u substitution would explicitly not work.
I see.
Yeah. This one, you're going to have to do something a little sneaky. And actually, what you do, which would be sneaky, is kind of explained why there's a failure of integration by parts here. So why would, not integration, why a failure of u substitution here? Why is there a failure of u substitution in this instance? Well, if I wanted to say u is equal to x squared plus or minus a squared, then du better be 2x dx. But there's no x on the outside here.
Right.
So the failure of this
Yeah, sorry, I didn't see that. I didn't see that.
is, well, it's all right. Because you know, this is a place of learning. We're allowed to. Integrals are very delicate. You kind of have to just get good at them by doing them, and it sucks because they're like extremely important to the foundation of modern science. So it would be nicer if there was like a completely unified theory of integration that was, you know, easy to state in elementary terms, but there's not really. And that's kind of the state of affairs with other things like differential equations. If you take a differential equations class at the university, you're going to focus on a tiny subset of differential equations with known analytic solutions or numerical methods of a solution to a differential equation, which is less satisfying. So yeah, it's the state of affairs. But the obstruction is that there is not this x here, and that is going to inform the kind of integration by parts you want to do. If we set this into dx, then that would be v equals x. And if we just left u as square root of plus or minus a squared, then du would be 2x square root x squared plus or minus a dx. No, that's incorrect. We would also have a 1/2 from this thing, and then the square root would be in the denominator. Wait. All right, I guess I'll stop trying to do fancy things and just write it out. So that becomes 1/2 times x squared plus or minus a squared to the minus 1/2 times, that's going to become 2x. Okay, so we just have x over squared x squared plus or minus a squared dx. This is still going to be fine from the perspective of a u substitution. Yeah, we'll get something that's fine. So we get that our integral is equal to x times the square root of x squared plus or minus a minus the integral of x squared dx over the square root of x squared plus or minus a. In this case, we can do a u substitution, so that u is equal to x squared plus or minus a squared. Then do we want to do it that way? So then du is equal to 2x dx. We want to split it up further. So we have an x squared. I'm going to rewrite this as x squared plus or minus a squared minus, then we have the integral x squared plus or minus a squared minus plus a squared over the square root of x squared plus or minus a squared dx. And then something tells me we've gone off course, but I'm going to keep going. I know that this is the correct substitution or integration by parts we have to make. Unless my derivative skills are just really awful. So then we have minus square root x squared plus or minus a squared. And then the minus sign here flips the plus minus here. So that should be dx plus or minus the integral of a squared over x squared plus or minus a squared square root dx. So maybe I should write out the arc derivative integrals. Well, this right here is the integral that we started with. So we should be able to end up solving an equation for this integral to find it, but we're going to have to integrate this thing. Here, let's pull this up. Let's just get a table of inverse trig functions. And we want to pull out an a from this. So this becomes plus or minus the integral of a over the square root, it should be dx, x over a squared plus or minus 1. It could be arcsinch or arccosh, or arc. It could be arcsine or arcsinch. this, then we have this. Do we want to rewrite it this way? Hmm. Apparently we should have been able to solve this integral already. Let's rewrite this way. Dx a. Then we have dx here. Um, let's see what happens if we solve it separately for plus and minus, and then do a trigonometric substitution. So if I have the integral of dx over the square root, if I say x over a is equal to tangent of x, I guess maybe I won't use the same variable. Is that going to work? Doing a trig substitution like that? Oh, that seems like it might be painful. So for a, dx, we set x over a to u. That tells us that dx over a equals du. So we can at least write it as du over square root of u squared plus or minus 1. If we had an a out here, so we have an a squared out here. Yeah, let's go with plus for now, because this actually isn't one of our inverse trig integrals. The u squared is in the wrong place. Just writing it neater, being redundant. Dang, this one's tough. Have we done that one already? And I completely forgot how to do it. It looks familiar to me. Be in a previous chapter.
Corbin,
Yeah, what's up?
I have to go.
Okay,
Sorry about that.
it's all right. I'll send you the video of this.
Thank you.
Yep.
Have a good day.
You too. Hmm. So if we said u is equal to tan theta, then du is equal to secant squared theta d theta. So then this becomes a squared times secant squared theta d theta over, I'm going to say this is for the plus version. That's going to, or the minus version. We want the minus version. For the minus version. So that is tan squared theta minus 1. So this is equal to a times, or a squared times the integral of secant theta d theta. And we figured out how to integrate secant theta, right? Let's see. This should be for the plus version. That should be for the plus version. So are we going to do an integration by parts again? So u equals secant theta v dv equals d theta. Mm. Yes, a squared over d theta over cosine theta. That substitution didn't seem like it helped at all.
Isn't this the one where you multiply by secant x plus tan x over secant x plus tan x?
That's right.
Or sorry, the thetas.
Yeah, the thetas. You do that trick. All right, all right. So we have a squared times secant squared theta plus secant theta tan theta. Theta. I swear, I've seen that trick so many times and I've forgotten it so many times. Plus tan theta. Then, oh, u is equal to secant theta plus tan theta. Du is equal to secant squared theta plus secant theta tan theta all times d theta. So this is equal to a squared times the integral of du over u equals a squared.
ln of secant x plus 10x. They're
Uh,
theta. Oh, I keep saying x.
It's all right. And then we need to keep in mind that theta is equal to arctan of x over a. So we get that this is equal to a squared theta du. Sorry. Oh, no more integrals. So that's going to be natural log of x over a plus. So x a is going to be square root of x squared plus a squared. Look at that. Oh, actually. Oh, no. We're good. We're good. Absolute value. So what we get is all the way up here, our integral is equal to, let's write this integral x squared plus or minus a squared dx is equal
Wait,
to,
isn't it just the plus case? It isn't plus or minus.
yep, we're just doing the plus case. The book says that we should be able to get the same answer either way. So we might have to try the minus case and show that we get the same answer, but we can do that in a second. So, and then we had minus the integral that we started with, x squared plus a squared dx. And then the minus canceled out here. So that should be plus a squared ln absolute value x over a plus square root x squared plus a squared. So we have twice the square root of x squared plus a squared dx is equal to x times the square root of x squared plus a squared. Got that here. Plus a squared ln absolute value of x over a plus square root x squared plus a squared. And then do we divide by 2? It seems likely, and yet that still seems wrong. Not dividing by 2, but the expression that we've obtained.
But this wouldn't work for the minus case, would it?
The book says that it does. We can try the minus case. There's another trig substitution that we can do.
Because like tan squared minus 1.
Yeah, we would
Is
just
that-
say u is equal to cotangent.
Oh, yeah.
So this is almost correct, except this thing right here. That shouldn't be there. Otherwise, we have the correct expression. Okay, so looking at this integral, I pulled an a out.
Wait, is the a supposed to still be there? Right there? At this part?
when you take the derivative with respect to x, since a is a constant, it just
Is a
passes
constant,
through.
so wait.
It's a coefficient of x, so it just passes through the derivative.
Oh, okay, wait. I read that as something. Okay, yeah, ignore me.
Dx over a. So I summoned an a to make this into a du. I have an a here, a squared. It's all correct except to right here.
Can you scroll down a little?
Yeah.
How did you get those terms from theta again?
So we said that u is equal to tan of theta. So theta is equal to arctan of u, but u is equal to x over a. So we have this triangle with a and then x. So the hypotenuse is square root of x squared plus a squared. And this is theta right here. So I plugged that into secant theta and tan. Ah, this is the worst. So right here, I multiplied by a squared over a squared. And passed this in here. So then I had 1 over a squared here. So let's rewrite this. X squared plus a squared. That is equal to a squared over a squared, x squared plus a squared is equal to a root x over a squared plus 1. Okay, so I did that correct. Because then I divided by an a, so we're just left with an a on the outside. Maybe there's a mistake. This is so we got this and I can't see an obvious mistake, and the book is really good. So we need to ask a third party. So one of your best friends in college will be, if you just type in internet or integral calculator into Google, the first result, integral-calculator.com, is extremely good.
Could the problem be from the thing that we started doing the plus like near the middle? Shouldn't we have like started with the plus case from the very beginning?
Well,
Would that
it
have changed
didn't
anything?
it didn't change anything until we tried to evaluate this denominator, the integral of this denominator.
Wait, can I see the original integral?
The integral calculator is actually agreeing with me. This is what the integral calculator says it should be. So in order to complete our discussion, then let's just do the minus case and show that we would get the same antiderivative anyway. Is it agreeing with me? Let's look at this answer one more time. Oh, it looks like the integral calculator is disagreeing with me in a certain way. What? It's equal to arctan of u. I forgot to write a plus c, which could actually be nice for us. We could make this antiderivative look nicer, but with that plus c in mind. But now the integral calculator is telling me I should have had an a out here as well. Not an a squared, just an a. Does he have an a there? He doesn't. If we wanted to get rid of that over a, we could have x squared ln, and then we multiply by a like this. Square root x squared plus a squared. And then we would have a squared ln x plus a square root x squared plus a, and then times 1 over a. So we could just subtract ln of 1 over a, or add ln of 1 over a to c, and that would be just another constant c. So we could do it that way, but that would just move it from the denominator of one to the numerator of the other. All right. I guess I will figure out what's wrong with this integral. Let's do it for the minus case. Show we get the same thing. And then I'll let you go for the evening. I'm it's so close. All right. Do dx over square root of x squared x over a squared minus 1. So we say that x over a is equal to cotan. Is cotan the one we want? let's see. So if we divide by sine, then we get cotan plus 1 is equal to cosecant squared. Yeah, cotan squared plus 1 is equal to cosecant squared. So we want this to be cosecant of theta. So then we get, oof, dang, I might take a triple L right now. That's not the right substitution. Yeah, let's see. Let's see. Cos squared theta plus sine squared theta is equal to 1. Divide by sine squared theta. So we get cot squared theta plus 1 is equal to cosecant squared theta. Let's try hyperbolic tangent then. X over A is equal to arc, sorry, is equal to tan of theta, arc tangent of theta. Let's try that. So dx over A is equal to sec squared of theta d theta. So we get sec squared theta d theta times A divided by square root of tanh squared theta minus 1. Okay, so yeah, it's equal to A times sec theta d theta. And then this is an integral we just have to know the stupid trick for. Sec theta plus tanh theta, or sec theta plus tan theta. And then we say u equal to sec theta tan theta. So we get A times the integral of du over u is equal to A ln of sec theta plus tan theta. And so we said before that x over A is equal to tan theta, which is the same thing as saying theta is equal to arctan of x over A. So if we draw our rectangle, we have x, A. So this is equal to A squared minus x squared. Oh boy, that's not good. Not looking good. We might have to use hyperbolic cotangent. All right. I will do this. I will do this next week. Or I might even make a video about it and then just send it to you guys. But I actually haven't eaten all day and I'm really hungry. So I will let you go and get whatever's going on here and in the negative case figured out.
Bye. Thanks.
Later.